Have you ever flipped a switch and thought about what happens in that tiny, tiny moment before the light actually comes on? We all think of electricity as being instantaneous, right? But here's the thing. Deep inside the circuits of pretty much every device you own, there's a hidden and totally predictable delay. So let's dive into the secret world of what I like to call electrical inertia.
Okay, so look at this. On one side, you've got a super simple circuit, just a resistor. You flip the switch and boom, the light is on, instantly. But if you introduce a couple of other very common components, suddenly you get a delay. The light doesn't just snap on, it kind of fades in. Now, it's the same electricity, it's the same switch, so what in the world is going on? And that right there, that's the big mystery we're going to solve today. Why isn't everything in the world of electronics just instant? What is physically happening inside those components that puts the brakes on electricity? The answer, it turns out, is really cool. To get to the bottom of this mystery, we need to introduce our two main suspects. Now, these components, they might look simple, but they have this really special property. They don't just let energy pass through them, they actually store it. And trust me, that changes everything. So let's meet our culprits, the capacitor and the inductor. First up, we have the capacitor. You know, the best way to think about a capacitor is to imagine it's a small water tank built into a pipe. You just can't fill that tank up instantly. It takes time for the water level, which is like our voltage, to rise. And you can't empty it in a split second either. So here's the key takeaway. A capacitor absolutely hates and fights against any sudden change in voltage. All right, our second suspect is the inductor. So if the capacitor is like a water tank, an inductor is like a big, heavy water wheel sitting in that same pipe. It takes some real effort to get that thing spinning, and once it's going, it really doesn't want to stop. It's got inertia, right? Well, inductors do the same thing. They resist any sudden change in the flow of electricity, or what we call current. And that, right there, is the heart of it all. Both of these components, they create a kind of electrical inertia. By storing energy, whether it's in an electric field or a magnetic field, they just fundamentally refuse to change instantly. And that resistance, that stubbornness against sudden change, well, that's the delay we're trying to figure out. So how do we actually prove this? Well, our first big clue comes from just watching what these circuits do all by themselves, with no power source pushing them around. We're going to peek at their natural behavior, their fade-out. So imagine this. We fill up our capacitor, our little water tank, and then we just disconnect the hose. What happens as it drains out through a resistor? That behavior, the way it naturally goes back to being empty, is what we call the circuit's natural response. It's like the circuit is showing us its true personality when nobody's looking. Now, this is where it gets really, really cool. Every single one of these circuits has its own unique speed, a specific rhythm for its fade-out. We call this the time constant, and we use the Greek letter tau for it. And it's actually a super simple calculation based on the parts in the circuit. For a capacitor circuit, it's just the resistance times the capacitance. This one little number is the key. It tells us everything about how long that delay is going to be. Okay, let's actually see this in action. We've got a graph here. The vertical axis, that's the voltage in our capacitor, and it's starting out fully charged. Along the bottom, the horizontal axis, is just time passing. Now, I want you to watch what happens when we just let it discharge. See that? It's not a straight line down, is it? It doesn't just fall off a cliff. It's this smooth, graceful, and perfectly predictable curve. The voltage fades away really fast at the beginning, but then it slows down as it gets closer and closer to zero. This shape, this exponential decay, is the signature of a natural response. So what does that time constant, that tau, actually mean when we look at this graph? Well, you can think of it as a special unit of time just for this circuit. After 1 tau has gone by, the circuit has already done most of its fading out. And by the time you get to about 5 of these taus, for all practical purposes, it's done. It's settled. It's like a universal ruler we can use to measure the speed of any of these circuits. Okay, so we've seen what the circuit does when we leave it alone, but what happens when we force it to change? Like when we flip a switch and connect a battery to it. Now this is where we get the circuit to confess all its secrets. So this scenario is called the step response. We're basically applying a sudden step up in voltage and then just watching to see how our circuit, with all its built-in inertia, responds. It can't jump there instantly, so it has to follow that same exact curve we just saw, but this time it's climbing up towards a new value instead of fading down to zero.
So how on earth can we predict this fade-in? Well, there's this incredible formula that describes it perfectly, but let's not get bogged down by the math. Just think of it like a universal recipe. It only uses 3 simple ingredients. And with those 3 things, we can predict exactly what the voltage or the current is going to be at any moment in time. Let's break down this recipe. It's so simple, we just need 3 things. First, the start value. What was the circuit doing right before we flipped the switch? Second, the final value. Where is this thing eventually going to settle down long after the change happens? And third, the speed. And that's just the time constant, our old friend tau, for the new circuit path. That's it. With those 3 things, we know everything. So we have our suspects. We have their motive, which is inertia. And now we have the recipe to predict exactly what they're going to do. I'd say it's time to apply this to a real case and finally close this investigation. All right, here's our scenario. We've got this circuit, and a switch has been closed for a really long time. Then, right at time 0, that switch suddenly opens. The big question is, what's the story of the capacitor's voltage from that exact moment onward? Let's use our recipe and find out. We're just going to follow the recipe step by step. 1, find the starting voltage. 2, find the final voltage. And 3, find the time constant for its new journey. Simple. Okay, step 1, the start value. So before that switch opened, the circuit was just sitting there, totally stable, which means the capacitor had plenty of time to fully charge up. And in this case, it was holding a steady 2,000 volts. That's our starting point. Next, step 2, the final value. After the switch opens, the capacitor finds itself in a new loop with a resistor that just leads to ground. There's no power source anymore. So where is it eventually going to end up? Well, it's going to discharge completely. Its final destination is 0 volts. And finally, step 3, the speed. How fast is this discharge going to happen? We just need to calculate the time constant for this new path. We multiply R times C, and we get a tau of 20 milliseconds. That's the unique speed of this specific fade-out. So now we take our 3 ingredients, our start value, our final value, and our speed, and we plug them into our universal recipe. And there it is, the complete story of that voltage over time. We started with just a simple question about a delay, and we've ended up with a perfect mathematical description of the future. The case is closed. But here's the final twist in the story. This delay, this electrical inertia, it's not some flaw that engineers have to work around. It is a fundamental tool that they use every single day. This predictable, controllable fade-out is the secret ingredient behind timers, audio filters, even the memory inside your computer. So the real question isn't why the delay exists. It's how has mastering that delay built the entire modern world.